In section 4.3, we're going to look at another really important application of the derivative, and that is to help us graph functions. We've already seen that the derivative can help us locate local max and min and absolute max and min, and that's part of what's really useful in figuring out the graph of a function, knowing those points, because those are important points on the graph. So we're going to include what we already learned about finding local max and min to help us in this section, but we're going to learn some other methods also that we can include along with that to help us get a more complete picture of what a graph of a function looks like. So one important thing that will help us in graphing a function is to figure out where the function is increasing and decreasing. And what we're going to see in this explanation here is that the derivative can give us that information. So if we look at the graph of this example function here in blue, we've picked a bunch of points on this curve and sketched the tangent line at those points. So we want to compare the tangent line to the graph itself. How can we relate the two? So notice between points A and B, the curve is increasing, right? Because as we move from left to right, it goes upward, which means it's increasing. Well, notice that on that section, all the tangent lines have positive slope. Same thing happens between points C and D. We have an increasing curve, and all the tangent lines have a positive slope. So here we've summarized that observation. Between those two sections we just described, the tangent lines have positive slope, meaning f prime is positive, right? Because the f prime represents the slope of the tangent. So if the tangent has a positive slope, then f prime would be positive. And we also saw these two segments corresponded to the function increasing. Now there's one other segment, and that is between B and C. You can see the blue curve is decreasing, so the function is decreasing in that segment. And if you look at the tangent lines, they all have negative slope, which means f prime, which represents the slope of the tangent, would be a negative number. So based on this observation, we can connect f prime being positive or negative to the function itself being increasing or decreasing. So here's that summary of that observation. If f prime is positive over some interval, then f is increasing on that interval. In the second part, if f prime is negative on some interval, then f is decreasing on that same interval. We're asked to find the intervals where this given function is increasing and decreasing. Let's start by sketching a graph, because this is an easy one to graph using methods of pre-calculus. We'll take the curve y equals x squared, and then that minus 3 means to shift it right 3 units. So the vertex was originally at the origin, but it will move over to 3 on the x-axis. So just a rough sketch looks like this, right? That same parabola shape, but now the whole thing is shifted right 3 units. So we can already answer the question based on this picture, right? So where is this increasing and decreasing? Well, this piece is decreasing, and then at 3, at the vertex here, it switches to increasing. But we always describe those using x intervals. So the decreasing part is for x less than 3. And as an interval, that means going from negative infinity on the left up to 3 on the right. So it's decreasing on the interval negative infinity to 3. And then the increasing piece is everything to the right of 3, right? That's the x interval corresponding to the increasing part. So that would go from 3 on the left to infinity on the right. Right, so we already know the answer, but let's see if we can use the derivative concept that we were just talking about to arrive at the same answer. So we know we're going to need to calculate f prime. So looking at our function, it's a composite function, so we need the chain rule. The outer function is the power function. So using the power rule, bring the 2 down in front, reduce the power from 2 down to 1, and then multiply by the derivative of the inside part. Well, the inside part is x minus 3. The derivative of that is just 1. And then simplifying by distributing the 2, we get 2x minus 6. Now we want to make the connection between f prime and where the graph is increasing and decreasing. So remember what we said was that f is increasing if f prime is positive. So to find that, take the formula for f prime and set it greater than 0. And then you can solve that inequality for x. So if we add 6 to both sides, get 2x greater than 6, and then divide by 2, we get x greater than 3. So we just made the connection that f is increasing whenever x is greater than 3. And in interval notation, that is from 3 to infinity. Okay, now let's look at where it's decreasing. Okay, so we know f is decreasing whenever the derivative is negative. So we're going to take our formula for f prime, and this time we set it less than 0 and solve for x. So we add 6, divide by 2, we get x less than 3. So this calculation tells us f is decreasing for x less than 3. And in interval notation, that means from negative infinity on the left up to 3 on the right. And notice these two results we just found are exactly the same as what we said over here just by looking at the graph. So in this case, I picked a very simple example because we could easily graph it and figure out the answer that way. That gave us a way to compare our results to make sure that they told us the right thing. But in most problems that you'll see, the function will be more complicated than this, and you won't know right away what the graph looks like. So you won't be able to just get the answer quickly by looking at the graph. Instead, you'll need to use this method of calculating the derivative and figuring out where the derivative is positive and negative. We'll also see in our other examples that determining where the derivative is positive and negative will sometimes be more work than it was here, but I wanted us to start with just a very simple example. Here's another example where we're asked to determine where this function is increasing and decreasing. So using the method we've been learning here, we need to find the derivative because it tells us about increasing and decreasing. We'll need to use the product rule here. So we take first times derivative of the second. Now the derivative of e to the x is e to the x. Then we have plus second times derivative of the first. So the derivative of x squared minus 3 is 2x minus 0, or just 2x. Now I'm going to simplify. Notice that both terms in the sum have e to the x, so I'm going to factor that out. And from the first term, that leaves x squared minus 3. And from the second term, it leaves plus 2x. So I'm going to summarize what f prime looks like here. We have e to the x times, and I'm going to put this in the more normal quadratic form, x squared plus 2x minus 3. So we need to now determine when this is positive and when it's negative. So One thing that would help with that is first finding the values of x that make it equal to 0, because 0 is the dividing point between being positive and negative. Okay, so that's going to be our next step, is find the zeros of f prime. And of course that terminology zeros just means find the values of x that make the formula output equal 0. So I'm going to take the formula for f prime and set it equal to 0, and then we'll try to solve for x. So you did this kind of equation solving a lot in pre-calculus, and since we have 0 on the right, what we like to do on the left is factor it as far as we can. So that quadratic expression in the parentheses can factor down to x plus 3 times x minus 1, and it still has the e to the x as another factor. And we have that product equal to 0. So anytime you have a product equal to 0, the next step is to set each individual factor equal to 0, and then solve each one of those individually. Okay, so from the top one, e to the x equals 0. There's no power of x that could make e to the x equal 0. Right? Even e to the 0 doesn't work, right? Because e to the 0 is 1. If you think about the graph of e to the x, it's always above the x-axis. It never crosses below. So e to the x is positive for all x. So this one has no solution. But we will get solutions from the other two. We'll get x equals negative 3 and x equals positive 1. So remember what these are. These are the zeros of f prime. In other words, if you plug either of these numbers into the formula for f prime, the output will be 0. Now here's the method we're going to use. We're going to create a number line, which is like our x-axis, and we're going to put our zeros on there. And I guess I should mention these zeros are also what we call critical numbers. Right? Remember, critical numbers are values that make f prime equal to 0. But they're also values that make f prime not exist. But if you look at this formula for f prime, this is defined for all x, right? There's never any problems of you can plug in any x you want into that formula. Okay, so we're not going to get any more critical numbers. If there were x's that made it undefined, we would want to include those in our list also of our critical numbers. So now on my number line, I'm going to list my critical numbers. So I have negative 3 and 1. So make sure you put them in order from smallest to biggest as you go left to right. And I don't want to put 0 on here unless it's a critical number. So this divides my x-axis into 3 subintervals. And we're going to test each subinterval to see if f prime is positive or negative over that subinterval. And so to do that, we can use a test point from each subinterval. So below the number line, I'm going to write my test points. So on the left subinterval, I can choose any number less than negative 3. So I'm going to choose negative 4. In the middle subinterval, choose any number between negative 3 and positive 1. So I'm going to choose 0. And then the right subinterval, any number greater than 1, I'm going to choose 2. Now we're going to take each test point and plug it into f prime. Now the formula for f prime you can see up here, but the factored form was this. So we're going to plug in to that. Okay, Okay, so I'm just going to make a note here. We're going to plug the test points into that formula. Okay, so let's start with our test point -4. When I plug -4 in here, I get e to the -4. Now, we were just discussing e to any power is positive. So that factor will be positive when I plug in -4. So I'm going to put a plus for that factor. Now I go to the second factor, x plus 3. When I plug in -4, I get -4 plus 3, which is -1. So it's a negative number. I don't really care that it's -1, I just care that it's negative. And then the third factor, when I plug in -4, I get -4 minus 1, which is negative. So I end up with the product of three numbers. One is positive and two are negative. So that product of those three signs will give me a positive result. So I'm going to put a plus up at the very top. Now we repeat this process for our next test point. When I plug 0 in here, e to the 0 is 1, which is positive. When I plug 0 into x plus 3, I get 3, which is positive. And when I plug 0 into 0 minus 1, I get -1, which is negative. So the product of those three signs, a plus, and a minus, will give me a negative result. And then the same process with the next test point, which is 2. When I plug 2 into e to the x, I get e squared, which is positive. 2 plus 3 is 5, is positive. And then 2 minus 1 is 1, which is positive. So the product of three positives is a positive result. So these signs on the top are the signs of f prime. So now we can use that to determine the intervals where f prime is increasing and where f is increasing and decreasing. Right? So we know that when f prime is positive, that means f itself is increasing. So we can say f is increasing on the intervals that have a positive value for f prime. So that would be everything to the left of -3, and then also everything to the right of 1. So I'm listing those two intervals in interval notation. And then we can say f is decreasing on any interval where f prime is negative, which would be this middle interval. So that is the interval from -3 to 1. So that's the basic method for how we determine where a function is increasing and decreasing using calculus. The first derivative gives us this information. I just wanted to mention that when I use this test point method, a couple of things to be careful about. One is your test points are never used as your endpoints of your intervals. They're always in the interior of the intervals. The intervals themselves are defined by these critical numbers. So they're the ones that could possibly be endpoints of your intervals. And notice over here we see the -3 and the 1 as endpoints. These three numbers, our test points, should never be endpoints of your intervals of increasing and decreasing. Another thing is, by factoring f prime, it let us do this type of calculation where we looked at products of factors and their signs. You don't have to do that, right? I could have taken -4 and plugged it into this version of f prime, or this version, right? Any version. It would just be a lot harder to calculate, right? If you plug -4 in for these x's and tried to simplify to determine whether it's positive or negative, is a lot more work. So by factoring it, it makes this process a lot easier to deal with. So last thing before we leave, if you used a calculator or computer to graph this function, you would see it looks something like this. Here's -3, here's 1, and the curve, try to get it as precise as I can. Something like this. This is what this function looks like. So we said it's increasing to the left of -3. Well, you can see that it's going up very slightly until we get to -3. And then it switches to decreasing between the x value -3 to the x value 1. That's this middle piece here where it's going down. And then it switches back to increasing when we get to the right of 1, and it stays increasing forever after that. So that matches this interval here. Here's the second part of this example. We have the same function that we were just looking at, but this time we're asked to find the local extrema. So we actually did most of the work to answer this question. So I'm going to put here a copy of this number line we made where we use the test points, right? We put our critical numbers on the as marked on the number line, and then we chose a test point in each subinterval, and then we plugged each test point into f prime to determine if f prime is positive or negative. So what we concluded last time, wherever we had a plus, that meant that f was increasing. And wherever we had a minus for f prime, that means that f is decreasing. So without even being very precise about the graph, we could do something like this. Start off with the function increasing. When we get to -3, it switches to decreasing. When we get to x-coordinate 1, it switches to increasing again. Notice that tells us we've got a local max right here, and we've got a local min at this point. And another thing we know is that the local max occurs at x-coordinate -3, right? Because it was at this x-coordinate that the graph switched from increasing to decreasing. And when you switch from increasing to decreasing, that creates a local max. And then the local min, it switched from decreasing to increasing at x-coordinate 1. That's what creates a local min. So at x-coordinate 1 is where our local min is. So we didn't find the y-coordinates, but we could, right? If you wanted to know the y-coordinate for our local max, which is at x-coordinate -3, to find the value of that local max, it's just the y-coordinate associated with -3. So you would plug -3 back into the original function. So make sure you're not plugging into f prime here, but into the actual function f. So the formula for f, I'll just put it up at the top. Oh, we already have it here. It's this x² - 3 times e to the x. So if we plug in -3 for x, we get 9 minus 3 times e to the -3. And that simplifies to 6 times e to the -3. You could put that in your calculator if you wanted a decimal for that. And then you could do the same thing for our local min, which occurred at x value 1. To find the value of that local min, just plug 1 into f. And we get 1 minus 3 times e to the first power, and that simplifies to negative 2e. So that's the y-coordinate of that local min. So this is an important use or discovery about how we can find local extrema by first determining where the function's increasing and decreasing, and then look for where it switches from one to the other. If it switches from increasing to decreasing, that means you've got this sort of mountaintop here, so you have a local max. If you have a point where it switches from decreasing to increasing, that creates this valley bottom, and you have a local min. So there is at least one thing you need to check, and that is that your function is continuous. If your function's discontinuous, then these results, this strategy won't always work, because you could have it jump at one of these points and it wouldn't follow this pattern. But if it's a continuous function, this method will always work. The technique we used on that last example is described here in the first derivative test. So the name of the test reflects that we're using the first derivative in our method. So here's the summary. So you have a critical number c and a continuous function f. Right? We emphasized earlier that it has to be continuous for this to work, because otherwise it might jump and not follow the mountaintop valley bottom situation we were describing. So part A says if f prime changes from positive to negative at c, so positive means increasing, negative means decreasing, so it switches from increasing to decreasing, then you've got that mountain peak or a local maximum at c. Part B is the opposite. F prime changes from negative to positive. So that if f prime is negative, that means f is decreasing, and then f prime positive means f is increasing. So changing from decreasing to increasing, we've got a valley bottom or a local minimum at c. And then the third possibility is at your critical point c, it might be that f prime is positive on both sides. So the subinterval to the left, f prime is positive, and the subinterval to the right of c is also f prime is positive. That means at c it changes from increasing, and it doesn't change, actually it stays increasing. That means there's not a local max or min at c. Or it could be that f prime is negative on both sides of c. Same situation. If either one of those happens, then your critical number turns out not to be a local max or a local min. And we saw that's possible with the graph of x cubed. Right, the shape of x cubed is this. 0 is a critical number because the tangent is horizontal there. But notice it's increasing on both sides. To the left of 0 and to the right of 0, the graph is increasing. So even though there's a critical number there, it turned out not to be a local extremum at that point. Here's another example. We're given a formula for a function, and in part A we want to find where it's increasing and decreasing, and then part B, find the local maxima and minima. So we know we can use our work from part A to help us answer part B. So part A is similar to the last couple of examples we did. We know we're going to need to find g prime. So because it's a difference, we can just take the derivative of each term individually. With x to the 4/3, we use the power rule. So we bring the 4/3 down in front, reduce the power by 1. So 4/3 minus 1 is the same as 4/3 minus 3/3, which is 1/3. On the second term, we've got minus 4. We just carry along the 4. Now the derivative of x to the 1/3, we use the power rule. So we bring the 1/3 down in front, reduce the power by 1. So 1/3 minus 3/3 is negative 2/3. Now let's simplify this. I'll keep the first term as it is. And then the second term we could write as minus 4/3 and could bring the x to the negative 2/3, could bring it down to the denominator and make it a positive 2/3. Okay, so that's fine. You could simplify differently, but I think this will work for our g prime. Now, using this number line method, we need to find the critical numbers because they're the points that we put on the number line. Okay, so we've had some practice with finding critical numbers. You want two things to check. Find values that make your derivative equal to 0. And then once we finish that, we'll find if there are any values that make g prime undefined. So I'm going to take the formula for g prime that we just found and set it equal to 0. And then we want to solve this for x. So I'm going to keep the first term on the left, and then I'm going to move the second term to the right by adding. Okay, now I can cancel out the 4/3 on both sides. By one way you could do that, multiply both sides by 3/4. So the left side becomes x to the 1/3. Right side is now just 1 over x to the 2/3. Now I'm going to multiply both sides by x to the 2/3. So on the right, I'll have x to the 1/3 is already there, and then we're multiplying by x to the 2/3. Right side becomes just 1. Now on the left, in that situation, we add the exponents. So 1/3 plus 2/3 is 3/3, so it's just x to the first power, and on the right, it's 1. So this is a critical number that came from our first case. It makes g prime equal to 0. The second way to get a critical number is values that make g prime undefined. Now look back at the formula we had for g prime up here. This first term, where x to the 1/3 is like cube root of x, you can take the cube root of any number, positive, negative, or 0. So this is defined for all x. But over here we've got an x in the denominator. So any value of x that makes the denominator 0 would make this formula undefined. And so that would be when x is 0, that would result in a 0 in the denominator. So it's undefined if x is 0. So that's another critical number. So we found two critical numbers. So we'll go to the next slide to continue, but the next thing we're going to do is to create our number line, and we put our critical numbers on the number line. So continuing with this example, I copied the original function g of x up at the top, and then I also wrote what we had found for g prime of x. Now before I make the number line and put our critical numbers on it, remember when we create our test points on our number line, we're going to plug them into g prime, and it really helps if g prime is in factored form. So let's see if we can get this factored so it's a product rather than a difference. So one thing I could do is factor out 4/3, because it's common to both terms. And that leaves x to the 1/3 in the first term, and then minus 1 over x to the 2/3, but I could go back to a negative exponent and write that as x to the negative 2/3. So then I'm going to factor out x to the negative 2/3. So we still have the 4/3. Now I'm going to factor out x to the negative 2/3, right? We usually factor out the smaller power, and negative 2/3 is less than 1/3. Now let's figure out what's left. So when we pull out negative 2/3 from this, let's think about what's left. So whatever we put here, we want the product with x to the negative 2/3 and this other number to become x to the 1/3. So that means when we add the two exponents, we want the sum to be 1/3. Well, that means we need this exponent to be 3/3, which is 1. So what's left here is x. Now let's go to the second term. When we factor out x to the negative 2/3 from this term, we're left with 1, and then there's a minus in front of it. So minus 1 here. Okay, so now let's write our final version of g prime. Now, if you wanted, we could move that x to the negative exponent down to the denominator. So in the numerator, we have 4 times x minus 1. And in the denominator, we have 3 times x to the positive 2/3. Okay, so this is a nice factored form of g prime. It's written as a product and difference, or sorry, product and quotient of factors rather than a difference in its original form. Now let's go to our number line. So we're going to put our critical numbers on it. So we found those on the previous slide to be 0 and 1. So put them in order from smallest to biggest as you go left to right. Then we choose our test points. So this one created 3 subintervals. We need a test point in each one. So over here we pick any number less than 0. So I'll choose -1. And then we need a number between 0 and 1, so I'll use 1/2. And then any number bigger than 1, I'll choose 2. So then we're going to plug those in to g prime, which the factored form of g prime is there. So let's start with the -1. In the numerator, 4 is always positive, so that's not going to make any difference. And then -1 minus 1 is a negative number. So the numerator is negative. In the denominator, when you plug in -1, the over 3 here means take the cube root. So the cube root of -1 is -1. But then the 2 here means square it. So when you square -1, you get, of course, +1. So we just determined when we plugged in -1, the numerator is negative and the denominator is positive. So I'll put negative over positive. So a negative number divided by a positive number gives a negative result. Now we're going to do the same process with our next test point, 1/2. In the numerator, 1/2 minus 1 is negative. Multiplying by 4 won't change that, it's still negative. And then 1/2 to a power, of course, will be positive. So the numerator is negative, denominator positive. And again, a negative over a positive gives a negative result. And our last test point, 2, when we plug it into the numerator, we get a positive, and then 2 to a power is always positive. So numerator and denominator both turned out to be positive. So the overall result is positive. So now let's answer part A, where it's increasing and decreasing. So our function g is increasing on any intervals where we put a plus, right? If g prime is positive, that means g is increasing. So the interval is to the right of 1. So in interval notation, that's 1 to infinity. And that's the only interval where we had a plus for g prime. And then g is decreasing on any interval where we found g prime to be negative. So that would be that it's decreasing on this entire, it's really two subintervals put together. So for any x less than 1, we have decreasing. Okay, so negative infinity up to 1. Okay, so that answers part A. Now for part B, we're looking for local max and min. Remember there was a condition you have to check to use, let me back up. Here it's switched from decreasing to increasing, so we think there's probably a local min there. But you don't know for sure unless you can verify that your function, your original function, is continuous. So let's check before we make any conclusions in part B. Is g continuous? Well, g is built of several parts. One part is x to the 1/3. That's the cube root function, and you should be familiar with that graph from pre-calculus. We haven't seen it a lot, but you would have seen it at some point. It basically looks like x cubed, but laying on its side, and that is continuous. Right? If you're more familiar with the graph of y equals x cubed, it's clearly continuous. Now, what about x to the 4/3? Well, you could view that as x to the 1/3 multiplied by itself 4 times. And I'm doing that because we know x to the 1/3 is continuous. And this is a product of continuous functions. So we learned that if two functions are continuous, then their product is continuous. So that means x to the 4/3 is also continuous. Then we have 4 times x to the 1/3. Well, if x to the 1/3 is continuous, when you multiply by a constant, it's still continuous. And then we have a difference of two continuous functions. We had a theorem earlier that said if you take two continuous functions, then their sum or difference or product are all continuous. So putting all that together without writing out every word, we conclude this function g is continuous. So we need to check that because otherwise our conclusion may not be correct that we're about to make. So, I was just hinting at it earlier, we switch from decreasing to increasing at x coordinate 1. All right, so if I make a curve that shows that, decreasing to increasing right here, we've got a local min at x coordinate 1. So that's our answer to part B. We could find the y coordinate if we wanted. Wouldn't be very hard. It would just be the value of this local min would be g evaluated at 1. And you see the formula for g up at the top, so it would be 1 minus 4, which is negative 3. And then we'll finish this just by looking at a graph. So I'll squeeze it in where I can find some space. So you wouldn't be expected to know this graph at this point, but if you had a computer graph it for you, you would see something like this. That's the basic shape. And this point here is the ordered pair 1, -3. Right, so in other words, x coordinate 1 is right above that point. So let's check the increasing, decreasing part. So we said decreasing to the left of 1, increasing to the right of 1. We can see that here, right? 1 is the point where it switches. Decreasing when we're on the left, increasing when we're on the right. You can also see this is a local min, just like we identified here. But one thing I want to point out was this other critical number, 0. 0 was a critical number, but it turned out not to be a local min or max because g is decreasing on either side of 0. So decreasing to the left of 0, and then when we cross to the right of 0, still decreasing. Notice there appears to be a vertical tangent there. And if you remember when we found our critical numbers, x equal 1 was a value where the derivative was 0, and you can see the slope of the tangent there would be 0. It's a horizontal tangent. But x equals 0 came from g prime being undefined, and that's because it was infinity. It had 0 in the denominator, and that means we have a vertical tangent at that point. But it turned out not to be a local max or min at that point. Here we're asked to find the local max and min values of the given function, and it's restricted to the interval 0 to 2 pi. So this is kind of like the part B of the last example. So even though this one doesn't ask us to find where it's increasing and decreasing, we need that in order to answer this question. So we're going to approach this problem exactly like the last problem. We'll start with the finding where it's increasing and decreasing using the number line method. So we need critical points, which means we need g prime. So derivative of x is 1. Then we have plus 2 times the derivative of sine is cosine. So then we look for our critical numbers by looking at two things. First of all, when g prime equals 0. So we set our formula we found for g prime equal to 0 and solve this for x. So first we'll subtract 1 and then divide by 2. And now you have to know your trig in order to answer this, to solve this from here. If you think about your unit circle, we want to find points on the unit circle where cosine is -1/2. Now remember, cosine is the x-coordinate of your point on the unit circle. So on our x-axis, -1/2 would be here. And if you move vertically, there's 2 points on the unit circle that have x-coordinate -1/2. It doesn't matter what the y-coordinate is. So then the question is, do you know what angle takes you, first of all, to this point? So this is a familiar point from the unit circle. It's one of the ones we memorized. The y-coordinate here is actually √3/2. And so you need to know the angle that takes you there, and that would be 2 pi thirds. And then same question for this other point. What angle takes you to that point? Well, if we count around in units of pi thirds, there's 1, 2, 3, 4 pi thirds. So the angle that I kind of marked in purple is 4 pi thirds. So there's two solutions, right? Because in this equation here, x represents the angle. So there's two solutions in one rotation around the circle. There's more if you keep going around, but we're limited to one time around the circle. And we found two values for x that work here. 2 pi thirds and 4 pi thirds. So these are both critical numbers. Then the second thing we look at are values that make g prime undefined. Let's look at our formula for g prime. Cosine x is defined for all x, so that means g prime here is defined for all x, so we don't get anything for that condition. So we just have the two critical numbers. So the next thing we do is create our number line and put our critical numbers on it in order from smallest to biggest. So 2 pi over 3 to the left, 4 pi over 3 to the right. Then we're going to choose our test points in each subinterval. So how about we choose 0 to the left. In the middle would be 3 pi thirds, which is the same as pi. That's a good test point there. And to the right, any number bigger than 4 pi over 3. We could go all the way to 2 pi if we wanted. I think that will be okay. Now, we look at our formula for g prime. That's where we're going to plug these in. And we like to factor it if possible, but this doesn't really factor, right? So we're just going to have to calculate. So if we plug 0 in, let's do these calculations over here. G prime evaluated at our first test point 0 will be 1 plus 2 times cosine of 0. Cosine of 0 is 1. So this is just 1 plus 2, which is 3. And notice that's a positive number, so we'll just put a plus. Now let's plug in pi into g prime. So here's again our formula for g prime where I'm plugging in. So 1 plus 2 times cosine of pi. Cosine of pi is negative 1. So that becomes 1 minus 2, which is negative 1. So we got a negative result when we plugged in that test point. And then we'll go to 2 pi, plug it into g prime. That's 1 plus cosine of 2 pi. Cosine of 2 pi, oh, I forgot the 2 out in front. Cosine of 2 pi is 1. So this simplifies to 1 plus 2, which is 3, which is a positive number. Okay, so now we can visualize, well, we can write in where it's increasing and decreasing, right? So positive means increasing, negative means decreasing. And if you visualize the curve, it starts out increasing. When we get to this point, switches to decreasing. Over at the next point, it comes in decreasing. When we get to 4 pi thirds, switches to increasing. So that tells us where our local max and min are. So we can see we have a local max at x equal 2 pi over 3. If you wanted to know the value of that local max, it just means find the corresponding y coordinate. Make sure you plug back into the original function, not the derivative. So it would be 2 pi over 3 plus 2 times sine of 2 pi over 3. And you could simplify that. I don't think I have space to do that. I'll just say find g of 2 pi over 3. And then we have at 4 pi thirds, you can see in our picture, it switches from decreasing to increasing. That makes that a local min at this x coordinate, 4 pi over 3. Okay, so we've done several examples now with some different types of functions. So this is the kind of problem that just takes a fair amount of practice. So make sure you spend some time working through the homework on these and then picking extra problems as needed to get more practice. So what we just learned with the first derivative test is very helpful if we were trying to figure out the graph of a function, right? If we were given a formula and we wanted to graph that formula, being able to determine where the function's increasing and decreasing is an important step. But it doesn't tell us everything. And the graph shown here it gives us an example of something the first derivative test wouldn't tell us. Suppose the first derivative test tells us the function's increasing, and suppose we even have 2 points, A and B, and we know it's increasing in between those 2 points. Both of these functions do that, right? They're both increasing over the same interval, but they're very different shape. We describe this difference in the shape as the concavity. So the graph on the left, we refer to this kind of shape where it looks like it's part of an upright bowl. We call this concave up. And the graph on the right looks like it's part of an upside down bowl. We call this concave down. Now there's a more technical definition of these two terms, which I'll give on the next slide. But that's a very intuitive way to think about those terms, just to get a big picture of what those terms mean. Here's the more technical definition for concave up and down. So notice on this curve we picked several points and we've sketched tangent lines. And we did the same thing on the other curve. And notice what's different. On the graph on the left, the curve itself that's in blue is always above the tangent lines. Whereas the graph on the right, the curve is always below the tangent lines. Okay, so if the curve lies above the tangent lines, like here on the left, we refer to that graph as being concave up. And then the other scenario on the right, if the curve lies below the tangent lines, that's the definition of the curve being concave down. So what we'll see is that f prime will not tell us about the concavity. So the first derivative test does not answer that question. We're going to learn that the second derivative, though, will tell us where the graph is concave up and concave down. This is an example of a graph of some function, and I wanted to point out that a function can switch concavity at different points on its graph. So notice when we start off on the left, this is like an upside down bowl, so this piece is concave down. But somewhere in this region you can see it's switched. This is like an upright bowl, so this part's concave up. So you try to locate the point where it switches, and so that point is marked B. Notice if I'm to the left of that point B, the bowl looks upside down, and if I'm to the right of point B, the bowl looks right side up. Then it continues being concave up for a while, and then you can see somewhere it's switched. This piece here is concave down. You can see I've labeled that, or it's been labeled here. And then there's this corner, and then to the right of this point it switches again. This is upright bowl, concave up. And then notice here there's a corner, and then on the other side it's still concave up. This is part of an upright bowl. And then somewhere in between, somewhere along the way it switches, because now here it's upside down bowl, concave down, and you could then try to identify the point, and here at point P is where it switches. Now all of this could be described in terms of tangents, right? So over here the curve lies below the tangents. That's the definition of concave down. In this piece, the curve lies above its tangent lines. Definition of concave up, right? You could do that all the way through. Okay, so another important thing to realize is these terms apply over intervals. So on the interval AB, or let's do it this way. We could say the curve is concave up on the following intervals. So we see here from x coordinate B to C, and then again from D to E and E to P. Just list those out. So we had A to B. Oh, sorry, that was concave down. The first concave up interval was B to C. And then we had one from D to E and another from E to P. And then it's concave down on some other intervals. So here we had A to B, the next one C to D, and then we had a third one from P to Q. So when we talk about concavity, just like with increasing and decreasing, it's always described as being over intervals. We spent all of today talking about part of section 4.3, what derivatives tell us about the shape of a graph. So we started by introducing the first derivative test, and this test tells us how to use the derivative of a function to determine where the function itself is increasing and decreasing. So that's an important thing to know about understanding the shape of a graph. We also saw how we could use the results from that same test to help find local max and min. And then right at the end, today we introduced the concept of concavity relating to the shape of a graph. And we mentioned that the first derivative will not tell us about concavity. So next time we're going to learn how the second derivative of a function will help us determine where a graph is concave up and where it's concave down. So we're spending a long time on this section because this is a very important section that one of the really useful applications of calculus in helping to determine the shape of a graph.